Welcome back, guys, and furthering on from our tutorial on proof by induction for the sum of a series, we're now going to be looking at proof by induction for divisibility. Okay, so we're going to look through example 4, 5 and 6, and we're going to look at the method that's used that's common for proof by divisibility. So example 4 says, prove that for all n is an element of n, and again we can see that this n stands for our natural numbers, which are our positive whole numbers. Prove that 3 is a factor of 4 to the power of n minus 1. And if the fact that it says 3 is a factor is what's showing me that we need to use proof by induction for divisibility. So again, I'm going to use the exact same 3 steps. Step 1, we're going to prove true for n is equal to 1. Okay, so I'm going to take my terms here, which is 4 to the power of n minus 1, and instead of n I'm going to sub in 1, so I have 4 to the power of 1 minus 1, so I get 4 minus 1, which gives me 3. So I can say dot 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 true for n is equal to 1, because we know that 3 is divisible by 3, so 3 is a factor of 3. So now I'm going to move on to step 2. And step 2 here, we're going to assume true for n is equal to k. And as I've said in all the previous videos, for proof by induction, it's key that we write our steps. Now the way we're going to phrase this is 3 is a factor of 4 to the power of k minus 1 for all k is an element of n. Okay? Because now we're assuming that 4 to the power of k minus 1 can be divided by 3. It's divisible by 3 if 3 is a factor. So for step 3 now, we're going to prove true for n is equal to k plus 1. Which means what we're trying to prove is that 3 is a factor of 4 to the power of k plus 1 minus 1 for all k is an element of n. Okay, which means now in our proof we need to take this guy and simplify him using our laws of indices. So paying attention to our proof here now, we have 4 to the power of k plus 1 minus 1. By our rules of indices, that's the same as having 4 to the power of k by 4 to the power of 1 minus 1, which is the same as having 4 to the power of k by 4 minus 1. Now the trick here is instead of 4, I'm going to sub in 3 plus 1 minus 1, because I haven't changed the actual value, because 3 plus 1 is still 4. And then I'm going to multiply 4 to the power of k by each one. So 4 to the power of k by 3 gives me 3 by 4 to the power of k. 4 to the power of k by 1 gives me 4 to the power of k minus 1, which I'm going to put in brackets because this matches what I had in my assumption up here. So now I can say, therefore, 3 times 4 to the power of k is divisible by 3, because anything that's multiplied by 3 is divisible by 3, and 4 to the power of k minus 1 is divisible by 3, and to give our reason why, we know that we assumed this in our assumption, so I'm just going to put assumed in brackets. Okay, so now I can say, therefore, if each term is divisible by 3, I can say the whole thing is divisible by 3. So 3 by 4 to the power of k plus 4 to the power of k minus 1 is divisible by 3. And if these are both divisible by 3, 3 has to be a factor. So now I can say, therefore, it's true for n is equal to k plus 1. And if it's true for n is equal to k plus 1, so it's true for all n, where n is an element of our natural numbers. Okay, and that's example 4. So take a minute, guys, add it into your notes if you need to, and then we're going to move on to looking at example 5. Example 5 is similar, where it says prove by induction that 8 to the power of n minus 7n plus 6 is divisible by 7. And again, the fact that it says divisible by 7 shows me that we're using proof by induction for divisibility. and it tells me for all n is an element of n, so I know I'm looking at my natural numbers again. So for induction, again, we always start with the steps. So step 1 is we're going to prove true for n is equal to 1, which means I'm going to take the expression given in the question and I'm going to sub in 1 for n. So we have 8 to the power of n minus 7n plus 6, which gives me 8 to the power of 1 by minus 7 by 1 plus 6, which gives me 8 minus 7 plus 6, which gives me 7. So now I'm going to say ... true for n is equal to 1, because 7 is obviously divisible by 7. Then we're going to go for step 2. And a step 2 again is to assume true for n is equal to k. Okay? So now we have to say again, the same type of sentence as in the last example. 7 is a factor of 8 to the power of k minus 7 by k, which is 7k, plus 6 for all k is an element of n. Okay? And then we're moving on to step 3. So step 3 here, step 3 here, we need to prove true for n is equal to k plus 1. Okay? Which means we need to know what that looks like before we start trying to prove. Which means what we're trying to prove is that 7 is a factor of 8 to the power of k plus 1 minus 7 by k plus 1 plus 6 for all k is an element of n. And now we're going to look at our actual proof where we're going to again use our laws of indices. So in this one here, I'm going to have 8 to the power of k plus 1 minus 7 by k plus 1 plus 6. Well, 8 to the power of k plus 1 by our laws of indices is the same as having 8 to the power of k by 8. Minus 7 by k gives me minus 7k. Minus 7 by 1 gives me minus 7 plus 6. Using the same trick as we used in the last example, I'm going to change this 8 to 7 plus 1, which doesn't change his actual value, and multiply it by 8 to the power of k, which means I get 7 by 8 to the power of k. 8 to the power of k by 1 gives me 8 to the power of k, minus 7k minus 7 plus 6. And now I'm going to group some of these terms together. So I have 7 by 8 to the power of k, and in brackets I have 8 to the power of k minus 7k plus 6 minus 7. And the reason why I put these three terms in brackets together is because they match what's given in my assumption. So now I can say, therefore, 7 by 8 to the power of k is divisible by 7, because again we can see it's multiplied by 7, so it has to be divisible by 7. And so is minus 7. Okay? I can also say that 8 to the power of k minus 7k plus 6 is divisible by 7. And the reason why we know that expression is divisible by 7 is because we assumed it in our assumption in step 2. So I'm going to put assumed in my bracket. So now I can say, therefore, 7 times 8 to the power of k plus 8 to the power of k minus 7k plus 6 minus 7 is divisible by 7. Which means if that's divisible by 7, we can now say it's true for n is equal to k plus 1. So therefore, true for n is equal to k plus 1. So it's true for all values of n when n is a natural number, where n is an element of n. Okay? So again, guys, I want you to pause the video here to take a second to add example 5 into your notes before we move on to example 6. And now when you're ready, guys, we're going to move on to example 6. Example 6 is again going to be looking at proof by induction for divisibility. But you'll notice that in example 6, it just says show. It doesn't tell me to use proof by induction. So when we see the words divisibility, we need to know we need to be using proof by induction. So again, we're going to start with the same steps here. It says show that n by n plus 1 by n plus 2 is divisible by 3 for all n is an element of n. So writing out our steps, step 1, we're going to prove true for n is equal to 1. Okay, which means we're going to take the expression given in our question, which is n by n plus 1 by n, sorry guys, wrong colour, which is going to be n by n plus 1 by n plus 2, n plus 1 by n plus 2, and instead of n we're going to sub in 1, which means I have 1 by 1 plus 1 by 1 plus 2, which gives me 1 by 2 by 3, which gives me 6, which I know is divisible by 3 because 3 is one of its factors, so I say dot 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 true for n is equal to 1. Okay, then we move on to step 2, writing the steps every single time. So step 2 is we assume true for n is equal to k. Okay, so again now I'm going to take the same sentence that 3 is a factor of, and instead of n I'm using the letter k. K by k plus 1 by k plus 2 for all k is an element of n. And last one guys, step 3, we're going to prove true for n is equal to k plus 1. Okay, we're going to prove true for n is equal to k plus 1. So again I want to see what I'm trying to prove. So I'm trying to prove that 3 is going to be a factor of, instead of k I'm going to have k plus 1. K plus 1 would give me k plus 2, and k plus 1 plus 2 would give me k plus 3 for all k is an element of n. And all these steps are super important every time guys, because it is a proof, which is what we're now going to prove. So we're going to take the expression we just came up with in example in step 3. So I have k plus 1 by k plus 2 by k plus 3. And what I'm going to do here is I'm going to split my last bracket and multiply it by all the terms before. So I'm going to split my k plus 3 to multiply it by all the terms before. Which when I do that I get k by k plus 1 by k plus 2 plus 3 by k plus 1 by k plus 2. And now I can see a nice little short proof this time. K by k plus 1 by k plus 2 is divisible by 3, and I know it's divisible by 3 because it's assumed in step 2. So again I'm going to put in brackets assumed. We know that 3 by k plus 1 by k plus 2 also is divisible by 3 because it is a multiple of 3, so we know it has to be divisible by 3, which means we can say now therefore k by k plus 1 by k plus 2 plus 3 by k plus 1 by k plus 2 is divisible by 3. And if that's divisible by 3, we can say that it is going to be true. So therefore true for n is equal to k plus 1. So it's true for all values of n where n is an element of our natural numbers, where n is an element of n. And that's our last one guys for proof by induction using divisibility. So again, pause the video here, make sure all 3 examples are added into our notes copy, and then we're going to move on to our last type of proof by induction, which involves inequalities. Thanks very much guys, see you next time.